A dial bore gauge is a specialized measurement tool that allows you to quickly pick up internal diameters or IDs. You do not have to remove the tool from the board to read a measurement. In fact, you can quickly sweep the gauge up, down, and around a cylinder to look for any deviations in the diameter. These changes in dimension could be a result of a manufacturing error or from uneven wear of the bore, which is common with engine cylinders. While we will not be measuring engine components in this video, the dial bore gauge is a great practical application of the dial indicator, which is an incredibly versatile measurement tool. We can remove the dial indicator from the rest of the bore gauge and take a closer look at how it works. When you press on the plunger, the large dial moves clockwise. For every 50 thousandths of an inch the plunger moves, the dial completes a full revolution. Each graduation on the outermost scale is equal to 5/10 of a thousandth of an inch. This dial indicator is about in the middle of the road for precision. There are some dial indicators with graduations as small as 50 millionths of an inch. That would be about twice the precision of the micrometers we used in the previous video. For every 360 degrees the large dial moves, the small hand moves one tick on the main scale. There are 5 graduations total on the main scale, which means the dial indicator can measure at most 1/4 of an inch. This small measurement range means that dial indicators are not often used for the direct measurement of distances. Instead, they are used for comparative measurements, such as how a bore gauge works. The meaning of a comparative measurement will make more sense with some measuring examples. But first, let's go over the anatomy of the bore gauge. The dial indicator locks into the top of the handle. From the handle, we have the stem, and then we have the measuring head. On one side of the measuring head, we have the measuring contact needle. If I actuate the contact needle, watch what happens to the dial indicator. The movement of the measuring head's needle directly drives the plunger on the dial indicator. The max deflection of the dial indicator is 100 thousandths of an inch when the needle is completely depressed. On the other side of the measuring needle, we have the anvil, which is a fixed point that comes into contact with the opposite side of the bore being measured. The anvil is removable and can be swapped for different sizes. In addition to changing the anvils, which come in 200 thousandths increments, these small washers can be inserted between the anvil and measuring head prior to screwing on the collet nut to fill the gap between anvil sizes. This modularity is what allows the bore gauge to measure a range of different sizes, in this case 1.4 to 6 inches, when the actual measurement needle can only read a small 100 thousandths of an inch range. The anvil and washer combination depends on what you expect the size of the bore to be. The bore gauge is only able to measure a small range of diameters once the anvil and washers have been chosen. For this reason, you need some kind of information on the nominal size of the bore, whether this is a dimension drawing or a quick caliper measurement. Here I have an oversized 2-inch bore that I've machined. It's close to 2 inches, but slightly larger. For this reason, I have chosen the 2-inch anvil from the left side of the kit. I should point out that this dial gauge comes with 2 measuring heads. I'm using the smaller head, which supports the anvils on the left. For any measurements larger than 2 inches, you would want to use the larger head and anvils on the right. Perhaps this might be obvious, but the 2-inch anvil is not actually 2 inches in length. This is just the size you use for a 2-inch hole. The 100 thousandths measurement range will be centered about the specification of the anvil. So with a 2-inch anvil, I'm able to measure a bore that's approximately 1.950 inches to 2.050 inches. For this example, I know that my bore is oversized. So a measurement range that includes anything less than 2 inches limits my ability to measure oversized features. For this reason, I added the 50 thousandths washer to move my measurement range to approximately 2 inches to 2.1 inches. Now it's time to discuss using the dial indicator as a comparator. The measurements on the face of the indicator currently have no meaning. We need to zero out the gauge on a known diameter that falls within our measurement range. There is an expensive and precise way of doing this, and an alternative cheap and dirty way. We'll start with the most precise first. This is a 2-inch calibration ring gauge. Here you can see just how close the internal diameter is to 2 inches. After inserting the bore gauge, I want to rock it back and forth to find the smallest distance, which corresponds to that 2-inch known diameter. Remember how the dial indicator works. The more that the plunger is pressed, the farther the dial turns clockwise. The plunger is tied to the measuring needle, which will be pressed further and further as the bore gets smaller. It's a common mistake to assume that the measurement of the bore is getting larger as the dial turns clockwise. This confusion arises from the fact that the numbers on the dial indicator count up in the clockwise direction. Once I find the smallest distance, which is the diameter, I can zero out the dial indicator by turning the measurement face so that the reading on the indicator is 0 at this distance. I take note of the main scale, which is reading 0.1 inches. What this means is that whenever the dial indicator shows a measurement where the larger dial reads 0 and the shorthand reads 0.1, then the whole diameter is precisely 2 inches. In essence, we are comparing future readings back to the 2-inch calibration ring. Hence, the device is functioning as a comparator. Now we can take a measurement of this unknown bore. I insert the gauge and rock it back and forth to find the shortest distance. This is when the dial turns the farthest in the clockwise direction. So it looks like that shortest distance is at 10. So the red numbers are if you count to the left, counterclockwise, and the black numbers are if you're counting clockwise. Now next I check the main scale, which says it's still at about that 1 mark, but we haven't returned back to the 0. This means that the diameter of this bore is 10,000ths of an inch greater than the ID of that 2-inch calibration. So that puts us at 2.010 inches. I have another unknown bore, but I know this one deviates even farther from the 2-inch standard. Let's see what effect that has on the main scale. So it looks like the shortest distance is about 1,000ths of an inch to the left of that 0 mark. If you were looking just at the main dial, then you might think that this bore is just 1,000ths of an inch greater than that 2-inch gauge, giving a diameter of 2.001 inches. But that would be incorrect. If you look at the main scale, we haven't returned back to that 0.1 graduation. We're actually at 0.05. That means we have to add a whole nother 50,000ths of an inch to that 0.1 thousandths. You have to be careful with the main scale. Master ring gauges are very expensive, especially if you only need to measure a one-off part. So as promised, the quick and dirty way for zeroing a dial bore gauge is to use micrometers. Basically, you just clamp them down on whatever dimension you need, and then it's a bit precarious, but you try and hold the bore gauge between the anvil and the spindle of the micrometer while setting the 0. Now this is pretty tricky and should only be done in a pinch. You're going to lose 1,000ths or 2 of accuracy when you set a dial bore gauge this way. So this video covered how to take an internal diameter of a bore with a dial bore gauge, but perhaps the most important thing covered was the introduction to dial indicators. In more advanced videos, I will show you how to take measures of parallelism and concentricity with a dial indicator.